In this second vector video, I want to talk about unit vectors. And unit vectors are going to be vectors that have a magnitude of 1. So just imagine if we had a vector in standard position. I'm just going to send it up this way. Right? A vector of unit 1 is just going to be a vector that's only 1 unit in length, instead of however long this red vector is. And so to get my hands on that unit vector, what I'm going to do, my unit vector, which I'm going to denote with the letter U, is going to be simply equal to my vector, whether it's longer or shorter, divided by the magnitude of that vector. It's a pretty simple formula. If you've got a note card going with this, so you have all your formulas in one spot, this is definitely something you want to put on that note card. So let's try this with an actual vector. Hey, I got pretty close here. Let's act like this red vector right here is -512. I'm wanting to find this little bitty green vector that goes in the same direction as -512, but it is only 1 unit long. Okay, so my formula for this is to take my vector in this standard form and then divide it by the magnitude. Now, I might need a little bit of a refresher for the magnitude of a vector. Remember, if it's in that standard form, we're going to do a squared plus b squared and then take the square root of it. So it's very Pythagorean. And that's what's going to happen here. I'm going to take the square root of a squared plus b squared. Okay. Not a lot of math I can do at the top of this, but on bottom down here, I get 25 plus 144. Last I checked, that was going to be 169. I take the square root of that 169, and this one comes out nice. I'd rather not see decimals on this. Okay, so simplified square root would be the best. And then we can go from there. Now, from here, this is just a scalar multiplication from the last video. If you don't believe me, how about now? Dividing something by 13 is the same as if I distribute 1 over 13 through. And so that's going to give me the vector -5/13, 12/13. And that is this little bitty green vector right here. If you don't believe me, find the magnitude of this guy, and I bet you that it's 1. And so it has to be going in the same direction. Okay. Not too bad there. I got a couple of problems for you to practice with that on your own where you can check yourself. But there are 2 very special unit vectors that we like to talk about in pre-calculus. The first one is the unit vector I. Okay. The unit vector I is just the vector that goes straight out to the right on the positive x-axis 1 unit. Okay, and it has a terminal point right here at the point 1, 0. Okay, the other very special vector we're going to talk about is the unit vector j. Unit vector j goes up 1 unit and points directly at this point 0, 1 right here. Both of them are 1 unit long, and they're both really nice because they go 1 unit in either the positive direction to the right or the positive direction up. Right, keep that in mind. Because now what we're going to be able to do, now that we have these 2 special unit vectors, I and j, we're going to be able to rewrite vectors in a different form. Some books call it a linear combination form. They just say using vectors I and j. Okay? So I'm just going to try to guide you through what's going on with this. So we have this vector that's going up and to the right here. And so normally that vector would be pointing at the point AB, or we would also call it vector AB. But let's think about what's actually going on with this. This vector AB right here is composed of a bunch of little bitty vectors that are 1 unit long. Don't worry about these little tick marks down here. But if I was to make a bunch of vectors that are 1 unit long, and I made A of them, I have A times I unit vectors going to the right here. Well, what about going up? Remember, going up and down, those are a bunch of j vectors. They're little unit vectors going up until we get to the very tip of our vectors. And so I have B times j vectors. And the way this works, if I add up all of these vectors, it gives me the vector AI plus bj. And then this is going to be my linear combination form, or I guess it does call it linear combination form. I didn't see that earlier. So we're able to rewrite our vector in this form. So we have two different ways to write the same vector. Let's see how similar they work, though. I'm going to teach this just a little bit different than the book. Because yesterday we had this problem, and on the last video, whenever we watched the last video, we had this problem, and it wasn't too bad. We had a vector with an initial point and a terminal point. Okay? It had an initial point at, say, 2, negative 6, let's call it right there, and at negative 6, positive 6. I'm not with negative 6, negative 6, positive 6. So we have this vector running up right here. And what I want to do is I want to rewrite that vector in terms of I and j as a linear combination. I'm going to be a little bit different than the book on this because I think it's going to be easiest if I go ahead and write that vector in the component form with the pointed brackets. And remember, to do that, I'm going to do terminal minus initial. Okay, terminal minus initials of my x values, which will be negative 6 minus 2. And I'm going to do terminal minus initial of my y values, which will be 6 minus a negative 6. And so this is going to give me the vector negative 8 and 12. And so that's what this would be in component form. If I was to move this blue vector over, it would land right here. I'm trying to make this as easy as possible. If I'm going to write this as a linear combination, I can just write it as negative 8i plus 12j. It just means I had negative 8 little unit vectors going this way, obviously not to scale, and I had positive 12 little j vectors going up to the top right there. It's a different way of writing it, and I'm not going to be that picky about which way I see it, unless, of course, the problem's asking you to write it in terms of I and j. Okay, you try part B, hit pause on the video, and then I'll work it as well, and then we'll come back. Terminal minus initial, terminal minus initial, terminal minus initial. Get that in your head, all right? The best you can. Now, we can also go back. I think probably the funnest part that we did on the last video was we did all the scalar multiplication and addition subtraction with it. And so we can definitely work it the same way with these vectors, even though they're in terms of I and j. Now, you could go back and rewrite this as 2, negative 3, and work it just like we did, and you'll get full credit. But I'm going to work it with these i's and j's. It says find the sum of it. So I'm just going to take v1 plus v2. So that's going to be 2i minus 3j. And I'm going to add that to 4i plus 5j. And then from here, all I have is combining like terms. I get 6i plus 2j. And that would be my answer on this. Which would have gotten me the same thing if I would have just done component form from the get-go. I would have got 6 and then 2. That would get me full credit. But the problem doesn't specify. I'm not going to be too picky about it, but probably for what the book's doing, if the problem's written as a linear combination, they're going to give you an answer as a linear combination. So if you have i's and j's, your answer should be i's and j's. One more thing I want to talk about, and that's the vector components in terms of magnitude and direction. Okay? So they're going to give me a little bit different information, just some information about the vector, and I'm going to be able to write it as either component form, linear combination form, whichever way you feel comfortable with. If you guys were here, I'd ask you, and we would just work it that way. But let me go ahead and just tell you where these formulas are coming from. Okay, so we have this vector right here. I'm just going to call it vector v. Okay, and so how long this black line is right here, this black vector, of course, is the magnitude. Now, we know that that's composed of two different vectors. It has a horizontal component, and let me do green. It has a vertical component. Okay, I'm going to call this A, and, oh, well, I didn't call it A. I called it X and Y. My bad. X and Y. So if I'm looking to get my hands on X, imagine that this magnitude is going to be given to you. We can make up a number if we want to. I'm just going to work it just kind of generic right now. But suppose I'm looking to get my hands on this X down here. I'm going to be given a direction angle that it is pointing at down here. And so it forms a right triangle, and everything's going to just follow SOHCAHTOA that we've been doing all semester. And so I know that if I'm looking for this adjacent side right here, and I'm given the hypotenuse, this magnitude of V, then adjacent hypotenuse, that's going to be cosine. Cosine theta equals the adjacent side, x, over the hypotenuse, which is the magnitude of V. My goal is to get my hands on this x, so again, if you have a note card, it would be really helpful to have this blue box on it. That formula right there will spit out what my x component is on my vector. And that little blue box isn't going to go away. We get into polar coordinates, we're going to have something that looks very similar to that as well. All right, but what about this y right here? The only difference with this y is that I'm dealing with the opposite side and the hypotenuse. Well, we know good and well that the opposite and the hypotenuse is sine. If I simply multiply both sides by v, again, I'm going to get this crucial blue box right here. I want to have that handy. I want to have it on top of my homework, my note card, wherever it may be. I want to have that thing close so that I'm able to write it down. Now, down here is just kind of a summary of everything I've said, and just in case you have forgotten the magnitude formula right there, and you're able to use it. So let's try this. I erased part B. We'll just make one up because you know good and well in my class that always works out well. But let's just draw this so it halfway makes sense to us. Okay, so I've got a vector that is pointing away from the positive x-axis at an angle of 135 degrees. Okay? And so that's all the way around this way. And it has a length of 7. Now, if you want to, I want you to feel very comfortable. Go ahead and draw your triangle if that's what you need. You got your right triangle. You have your reference angle in here, theta, and you can go with it. And you can just simply do SOHCAHTOA with this, and you're going to get the right answer, I promise. I'll work it one way each. Okay, so let's just talk about finding out, switch my variables again. I think at some point in the past that I used a's and b's instead of x's and y's. So let's just find x first. Okay, according to my formula, it said x is equal to the magnitude of v cosine theta. Well, the magnitude of v, the length of that line is 7 units, and I am taking cosine of 135 degrees. I'll change it here in a minute, but cosine of 135 degrees is a nice angle. Therefore, I want an exact answer on there. Use your note card, unit circle, whatever you need. But if I take cosine of 135 degrees, that gives me negative square root of 2 over 2. And I combine like terms. Yeah, I'm going to want this nasty exact answer right there. Negative 7 square root of 2 over 2. So you might be saying, okay, all these formulas, I have no idea what's going on, Mr. Lovelady. And I'll say, okay, let's just rework this then. I'm wanting to figure out what y is. Y is my vertical component on here. And so if I'm looking for y, and I know the hypotenuse is 7, I have opposite over hypotenuse. Okay, so that's just going to be y divided by 7. If I'm wanting to solve this for y, all I'm doing is multiplying the 7 over to this side, and that will solve me for y. So I can still just do SOHCAHTOA on this. This theta right here is 135 degrees, so I still have 7 times, well, this time I'm in the stripper quadrant, and so that's going to be square root of 2 over 2. So 7 square root of 2 over 2. I've got both components. I'm ready to write my vector. Okay? So my vector is going to be negative 7 squared root of 2 over 2, and positive 7 squared root of 2 over 2. Or you might say, well, I need to practice my linear combination form. I can definitely write it negative 7 square roots of 2 over 2I plus 7 square roots of 2 over 2j. Either one's fine. But before we go, let's talk about what's not acceptable. I have a lot of people that like to mix and match these, and they're kind of comical to watch. I get negative 7 square root of 2 over 2I, comma, positive 7 square root of 2 over 2j. All right? Can't mix your pointed brackets and your i's and j's. Or they might say, okay, well, I understand. I don't need the comma right there. I need a plus sign. No, I can't have this plus sign with the brackets. It's either the brackets with the parenthesis, with the comma in between, or it's the i's and j's with the mathematical symbols, the plus minus in between. Okay, so don't mix and match those. Why don't you try one of these before we go? We'll just make one up, because that always works well. Fortunately, Nate's not here, so he's really good at coming up with the number 7, but I've already worked the number 7, so I don't really want to repeat that. So let's just say, I'll just kind of make it so it's nasty. I got a magnitude of 5.4. Okay, that's the magnitude of my vector, and it has a direction angle of, I don't know, 251 sound good? 251 degrees? I want a vector that will come off that will match that. So hit pause on the video and work this out, and I'll do the same. All right, here's what my calculator got me. Make sure it's in degrees when we're working this, because the angle they gave me is in degrees. Might have to float back and forth between them. And I'm just going to make sure my answer makes sense. If I was to just draw me a real quick XY axis, and I imagine going over maybe like 1 1/4, and then down a little over 5, I would have a vector, something close to this. Okay, that makes sense for it to be about 5.4 units long, and a direction angle about 251. Yeah, that looks good to be about 251 degrees, so I feel pretty confident in my answers. Okay. Here's some practice problems. Any questions you have over this, feel free to email me, and I'll keep you anonymous, and if I see it's a big problem, I'll post it to Google Classroom. If not, we can definitely go over this in the Q&A later this week.